Okay, let's talk through some of the information necessary to complete Lab 13. So we're looking at special relativity and time dilation. There's also something called length contraction, but I didn't have a simulation for that one. So we're just going to focus on time dilation for now. There's something called the Lorentz factor, and it's represented by the Greek letter gamma, and it's a complicated square root function, but we've got 1 over the square root of 1 minus the speed of the moving object divided by the speed of light, and then that ratio squared. Sometimes you'll see it as v squared over c squared, and that's the same thing. Occasionally you'll see this, and a lot of times this is from issues with formatting, but sometimes you'll see this all raised to the negative 1/2 power, and that's the same thing. So the negative part means that it was really in the bottom of the fraction, and the 1/2 is relative for the square root. So a few different ways that we can see this. The nice thing about this simulation and what we need for the first few questions is that we can actually just dial in a speed and then run the simulation and then see how the time has changed. So for the first part, we want to have 1/4 of the speed of light. So we can move this along to 0.25, which is obviously the same thing as 1/4, and then run it. And as 1 second passes inside of the spaceship, because it's moving so fast, we have time dilation. Basically, think of like stretching the definition of time. And somebody outside of the spaceship is actually going to think that more time has passed. And so we get 1.033 instead of 1. And the nice thing is, because this reference is just 1 second, then technically we have 1.033 divided by 1, which is just 1.033. Seconds and seconds would cancel, and that's the same thing you get from calculating manually. We're going to check this one just to see how the process works, but then we've got a couple that we can just run the simulation and see. Okay, so we're going to try this. We're going to have 1 divided by this giant square root, and if it's going 1/4 of the speed of light, then this ratio just turns into 1/4, because technically you'd have 1/4 c over c, and it would cancel, and then you run through the rest of it. So the 1/4, or if it's a decimal, will just go here, and then it gets squared. You can, if you're very careful, run this through a calculator all at once and see what it makes. But for a lot of calculators, that's pretty tricky and needs lots of additional parentheses. So we're just going to run through order of operations and see what this turns into. So 1/4 squared, it turns into 1/16, and if we divide 1 by 16 and make that a decimal, then we get 0.0625. Or you could turn this into a decimal first, 0.25, and then square that, and you get the same thing. Either way, I'm technically skipping one little bitty tiny step, but I think it's an easy enough one to follow, but that's going to be okay. Then we still don't really know what's going on with the fraction or the square root, but we can finish the stuff under the square root by doing that subtraction. So 0.9375. Then we can take the square root of that, and we get 1 over some horrible decimal, 0.968 245, and it just goes on and on. And then finally, taking the reciprocal of this, or manually doing 1 divided by that other number, gives us about 1.033, which thankfully matches. So it worked out. For our next question, we want to see what factor, relativistic factor, goes along with something moving half of the speed of light. So I move the little slider to half of the speed of light, and then we run it. So if 1 second passes inside there in the moving rocket that's going, super duper fast, half the speed of light, then somebody outside of the rocket is going to feel like 1.155 seconds has passed. So you may think that with double the speed, from 1/4 to 1/2, which is the same as 2/4, that we'd have double the time, but it ends up not working that way. So the factor increases, but it certainly isn't 2 point something. It's not double what it was earlier. Okay, and then We need 3/4 of the speed of light. So we'll dial in 0.75. I'm going to run one more of these. All right, so we could plug into that formula, or we can read from here that we end up getting a relativistic factor of 1.512. And the final question on the first page, did the values above increase linearly? So does that mean that 2/4 is twice the factor of 1/4 is 3/4, 3 times the factor? And as it turns out, no. This is triple the speed we had in the original example, and it's only about 50% more on the factor. Okay, then unfortunately, because these formulas are a bit complex in the first place, if we try to solve them around and do different things with them, basically everything is a little bit complicated to find. So we're going to try that now. We're going to rearrange some stuff and see what we can find. So we want to take this gamma formula for this Lorentz factor for moving close to the speed of light, and we want to resolve it for the speed. In particular, we really want the ratio of v over c, because once things get close to the speed of light, the actual regular number for the speed of the object matters less than just how close is it to the speed of light. Then to work this through, we need to fight through some algebra, but we can manipulate this a little bit to make it easier to look at. So if I say that this was gamma over 1, then I have what looks like a really horrible proportion, but is still technically would be a proportion. You can cross multiply and divide, or there's this weird rule with proportions that says you can swap your cross terms. So I can just change these out with each other, switch their places, and I can say that the square root stuff over 1 is equal to 1 over gamma. Now, the ones on the bottom aren't really going to be important, but I'm going to have to remember to keep 1 over gamma. Then the next thing I want to do is get rid of this square root, so I'm going to square both sides. Again, squaring the ones isn't really going to do anything. What that's going to do is it's going to free up the stuff under the square root, and then I'm going to have 1 over gamma squared. Now, for convenience and for writing stuff down, and then especially for typing things in formula sheets, it's probably going to be easier to say that this is gamma to the -2, where that negative exponent just means that it used to be on the bottom of a fraction. Notice that it still has a 2 for the number, but it turns negative on the exponent when we bring it to the normal part of the fraction. Okay, then from here, we want to finish solving, eventually getting to just v over c. So I'm going to rewrite that together on the next line and just swap colors to maybe make it a little bit easier to follow. But if we have 1 minus v over c squared equal to gamma to the -2, and I'm still looking for v over c, then I've got this 1 that's in the way. So I want to subtract by 1. Be careful with your signs. You don't want to forget that this would still be negative because it was minus v over c squared. But if I subtract 1, then I'm going to have -1 plus gamma to the -2. The order may seem weird here, but it's intentional for the signs that are about to flip. So technically now, I can either multiply or divide by -1, which is the same as just flipping all the signs, and then that makes the placement of the 1 make a little more sense. So we'd have v over c squared is equal to now a regular 1, positive 1, minus gamma to the -2. And then finally, I'd want to take the square root of this to get just v over c. And that's going to tell me that the ratio of the velocity compared to the speed of light is equal to the square root of 1 minus gamma to the -2. It's up to you exactly how you record this and how you use it in the future. So, remembering that this is to the -2 power on gamma, if you're writing this out by hand, it may be a little bit easier to think of it as gamma squared on the bottom of the fraction, but that comes down to personal preference and how you learn to type stuff in your calculator. Now, what we want to do first is we want to plug in a value for the relativistic factor. So we're going to plug in a number for gamma, and then we're going to see what that solves out to, and then we're going to check it from the simulation. And then after that, we can use the simulation to find a few more new numbers. So we'll do one by hand, and then we'll do some assisted with tools afterwards. Okay, so the first thing that we want to check, if gamma is 2, then we want to see what's going to happen with V over C. So we've got 1 minus 2 raised to the negative 2 power, which at first glance you're thinking 1 minus 2, we can't do that, it's going to be negative, there's a square root, but then we have to remember that weird exponent and what it means. And so if we do that, then this turns into 1 minus 1 over 2 squared, which again looks like the other format there. So like I said, these two are equivalent. Then that's going to be 1 minus 1 over 4 when you take the 2 squared. So that's the same as 0.25, which is the square root of 0.75. And then that would tell us that our ratio here is about 0.866. And then if we want that technically in terms of an actual speed, then sometimes we multiply by c. And that would be the same as saying that the velocity is 0.866 times the speed of light. Now let's check that and see. We can't dial in exactly that number, but if we dial in 0.87, which is just a tiny bit higher, and then we run it, then we want to see a relativistic factor that's just a hair over 2. Because remember, we overshot the number slightly. And sure enough, it works. Then for the next two questions, we want to try a relativistic factor of 4 and then 8. So we're going to double those up. And you might think naively that, okay, well, if I want twice the factor, I need twice the speed, but nothing can go faster than the speed of light. We can't have things even go that fast. Even this in simulation is, not something that could physically happen with technology we have, but it wouldn't happen at all to try to make something go like 1.74 times the speed of light. So it doesn't make sense. So what we're going to do is we're just going to scale it up some, maybe 0.95, and then see if this gets us to 4. So 87 to 95 might not seem like a big change, but you can see we already passed 2 a little while ago. And as it turns out, that wasn't actually enough. So we need to go up a little higher. Let's go 9.7 maybe. There it's passing 3. And then just a little past 4. Let's try 9.6. Obviously it'd be a little bit smaller, but I don't know if it's going to end up being less than 4. No, and actually there's a really big difference between those. So 9.7 is going to be our closest fit. If we calculate out manually, as it turns out, we get 0.968, but I don't have the ability to dial that in here. Okay, and then the last one on the page, number 8, we want to try to get a relativistic factor of 8. So, we're at 4, and we can only go to 1 as an absolute maximum. So we don't have a lot of room. In fact, this pegs out at 99, so we can't even get to 1.00. Let's try 98. So 97 to 98 may seem like a really tiny change, but you may notice where the rocket started on the simulation window compared to the other one. So we went from 4 to 5 just from moving one little notch. And then if I use my last notch, unfortunately that's as far as I can go. And let's see what this one gives us. Okay. We want 8. We only got to 7. We can't even quite get there. As it turns out, it's really, really close, and this gets really sensitive the closer that gets to the number 1. So the proper answer, according to my notes, is 0.992. And so that extra decimal place, technically is a 0 right now, but changing the third decimal place from a 0 to a 2 adds a whole number to the factor there. Once more, we want to see that these did not increase linearly. So you would think, you would have to double the speed to get double the factor, but as it turns out, we had smaller differences in the speeds as the gamma increases. So when gamma jumped from, 5 to 7 was only 0.98 to 0.99, very tiny changes there. This ends up working out because of the way gamma shows up in the formula. So gamma, it's probably easier to see in the second version. But gamma here, because it's 1 over gamma squared in this equation, then the bigger gamma gets because it's being divided and it's being squared, both things happen at the same time, then this answer starts to shrink very, very, very quickly. And then when this becomes very small, then the answer in here becomes very close to 1, and then some strange things happen. So then, unfortunately, the next part doesn't work very well when we're not all in the same room together. So what was supposed to happen is we'd have a hands-on activity where we'd all use our own numbers and then compare against each other and help each other calculate stuff. But that's not going to be possible with the particular format of this lab right now. So what we want to do, I'm going to clear away some space first. We're going to all use the same numbers. And I'm going to use the number instead of, it's supposed to be your own birthday, or I guess my own birthday if I was doing this in the classroom with people. But we're going to use America's birthday because, why not? So we're going to use as our time, our number that we want. We're going to use our reference as 0.0704, which would be July 4th for Independence Day. Then for an alternative number, because we're going to need to do a couple of different types of calculations here, we're going to just pick the last day of the year instead of the current day, because people might be doing these on different days. And so we'll just say 12.31 for December 31st. Okay, so these are going to be our reference numbers, and we're going to use these to calculate a few things and see where this goes. So one of our formulas from lecture, and should be on the formula sheet for lab as well, says that the observed time is equal to gamma multiplied by the proper time. So the observed time is what somebody outside of a spaceship would see, and somebody inside a spaceship is going really, really fast. And then the proper time is, what they actually feel inside the spaceship, how real time passes for them. We have to remember that we want to plug in for gamma, so that's up at the top. So we can sort of expand this a little bit. And trying to pick a color I haven't used yet. Gamma is, remember, 1 divided by the square root of 1 minus v over c squared, and then that would multiply by the proper time. Sometimes people even just take the T0 and stick it up top, and then divide by whatever that turns into. I like to leave it this way so that we can see what gamma actually ends up being for this, and then calculate from there. Okay, so if we're going to use v over c this time as that first number, and if we're going to make this our proper time following the instructions in question 14, then we have places for those things to go in this equation. So 1 over the big square root of 1 minus the decimal, so 0.0704 squared, because that's part of the original definition. And then whatever gamma factor that makes, then it's going to multiply by, so I'm going to put big parentheses to show that it multiplies by 12.31 seconds. So if somebody inside the spaceship would feel like 12.31 seconds have passed, but somebody outside the spaceship is going to feel a different amount of time in this formula. So let us see how much. Okay, so we'd want to remember follow through the order of operations. If you can type this in the formula all at once. You know, you need more parentheses, you got to be careful. What might be better is to square that up first and then do the subtraction and the square root, 1 divided by that. There's a few different ways, and it's going to change from calculator to calculator. So I'm going to leave that as something for you to practice because we've already seen this type of calculation from earlier. What we're going to have so far now, if we work down what this gamma factor is, then we get 1.00, oops, only 2 zeros though, 2, 4, 8, 7, so on, so on. It's got square roots involved and weird fractions, so this was always going to be ugly. And then that's going to be how much this scales up, which in the end ends up being not a whole lot. So this ends up being very, very small change of about 0.03 of a second difference. Okay, then if we wanted to go in the other direction, if we want to take this formula and flip it and reverse it and, you know, see what happens if somebody is watching and they're counting time and we want to see what the time was that really passed inside the spaceship, then we can do that, but we just have to write everything backwards. So what will happen then is we want to get the T0 by itself, which means that we would divide by gamma. So a T0 is equal to either T divided by gamma, or occasionally you'll see it as T multiplied by gamma to the negative first power, where again the negative exponent just means it should have been in the other part of a fraction. You can do this either way around, and it doesn't really matter how. The nice thing about gamma to the negative 1 is that originally, because gamma was something that had a fraction and some stuff under 1, then this just kind of flips around and actually makes this a little bit prettier. So we can say that T0 ends up being the, instead of 1 over the square root, just the square root of 1 minus V over C squared. And then that's going to multiply by T. So I guess to be consistent, we'll stick that in front. But yeah, gamma actually simplifies a little bit when it's gamma to the negative 1 because it gets part of the reciprocal fraction that we had in the first place. Okay, but if we're going to plug our numbers into this, if we're going to adjust our values and decide that now this was the observed time instead of T0 for the proper time, then these are going to plug in different ways, but still will be something that we can reasonably easily calculate. So I don't know what the proper time is. My observed time is now 12.31 seconds. Then the square root here, we have 1 minus V over C, which is that decimal, that ratio there. Except I accidentally skipped the 0, 0.0704. And we can't forget that this is going to get squared. So we want to work this down. It ends up being kind of similar to a gamma factor, except because it's the reciprocal to it, instead of being 1 point something or larger, it's actually going to be smaller. It's going to be some decimal. So if we run this through, then we'll get something like 0.997518 and blah, blah, blah. It just keeps going. It's going to fill up your calculator screen. But as long as you're careful in how you use your calculator, you shouldn't need to be typing that number in again. You just leave it on the calculator screen and then multiply by 12.31. And if we do that, we get something around 12.28. All right, then one more page in the lab assignment if you're following along on paper. And then if you're just running the quiz, just a couple questions left, we're almost done. Now we want to take the time equation and we want to resolve it for V over C. So let's see if we can find maybe the easiest place to do this. So I don't need these numbers on the bottom anymore, but yeah, I guess technically from here we could use this and solve. So if we look from this point and we're trying to get V over C by itself, then we want that T to go away. So we would divide by T. And that's going to tell us that T0 over T, so proper time divided by observed time, is equal to the square root of 1 minus V over C squared. Okay, but then keeping in mind that all that stuff's under a square root, then we're going to want to square it. So we'll have T0 squared over T squared, and then the square root's going to drop. We'll have 1 minus V over C squared. Okay, then we'll want to move this 1 out of the way, and we'll use a similar trick to before. So now this is going to be -1 plus T0 squared over T squared is equal to, and the reason we put the -1 out front is we still have a negative outside of the parentheses because the V over C squared was subtracted before. Then flipping all your signs or multiplying or dividing by -1 to clear through here is going to tell us that 1 minus T0 squared over T squared is equal to V over C squared. And then finally, we want to take the square root, and so we get that V over C, because now this is all by itself. I'll write it first because it's the answer, is the square root of just that whole chunk of stuff that was over here. So 1 minus T0, sorry, I'm going to fix my handwriting there, T0, I said I would fix it, I think I made it worse. All right, one more time, try T0 squared over T squared. Whatever, that'll work. My square root's a bit long, but that's fine. Occasionally, we'll see this in a very slightly different format, again, because the fractions are sometimes difficult to type in or to communicate digitally. So this is the same thing as 1 minus T0 squared. So notice that one didn't change because it was on the top of the fraction, but then times T to the -2. So it was squared, but it was from the bottom, and when we move it up, it becomes a negative exponent. So those are equivalent to each other. So we want to try to use that to calculate some numbers based off of our random dates from before. So I'm going to clear some of this out of the way. The 0.0704 is going to be our proper time, and then the dilated time is going to be the 12.31. So we'll plug into that in just a minute. And then we'll see how fast somebody would have to go to take about a 14th of a second and stretch that into about 12 1/3 seconds. Oops, actually I want that other version of this. There we go. Okay, so we want to use the formula here, and like I said, we want to use this for T0 for the proper time, and then we want to stretch that as an observed time of multiple seconds. So a very big change between these. Remember though that doesn't mean necessarily that we're going to get a very big number for our answer, because the speed of light is the ultimate speed limit. You can't go beyond that. What's going to happen though is we're going to end up getting very, very close to the speed of light. Okay, so let's try it and see what's going to happen here. We don't know V over C. Then we have some stuff to plug into it. We'll have 1 minus T0 squared is 0.0704. So we'll use the first version of this. I think is easier to write into right now. Divided by 12.31. And to save a little calculator work, it may be easier to divide those first and then square. It actually gives you the same answer. And doing that, divide these, then square them, then that's going to give you giant square root 1 minus 0.0000327 and so on, so on. So that's going to go really far out on the calculator. Depending on your calculator, it may even go into scientific notation. So it might tell you 3.2, if it doesn't round, 3.260614 or something like that, times 10 to the negative 5. So we don't use scientific notation a whole lot, but you do want to make sure you're still familiar with how to move back and forth between different number formats. All right, the next thing, we want to take 1 minus this number. And because it's a little bitty number, we're going to have a square root of something very close to 1. So 0.999, that's 4 nines, then 6729386, and then so on, so on. So the exact number of decimal places may change depending on your calculator. But, basically a whole bunch of nines first is going to be very, very close to 1. And then because of the way that square roots work, when we take the square root of this, it actually gets even closer to 1. So in the end, we see that V over C, our ratio to the velocity to the speed of light, is 0. Still 4 nines, but then it gets bigger. It goes from being a 6 to being an 8. It basically like cuts half the difference getting to 1. Then 3, 6, 4, 6, 7, and again, so on, so on. Which is going to, as far as our answer choices and what we pick, is going to be closest to 0.999984. So you would take at the very end, if you want the actual speed, multiply by the speed of light, the c, to bring this over. And then to get the real speed, which we're going to do in question 19, we take what the speed of light is. Now, a very slightly rounded number, but the speed of light is roughly 3 times 10 to the 8. So that means about 300 million meters per second. And so we would take the 0.99984 and multiply it by 3 times 10 to the 8 meters per second. And then that's going to give us about 299,995,000 meters per second. All right, then final part for the lab, we want to see how that turns into a kinetic energy. So we've had kinetic energies before, and we've had maybe thousands or tens of thousands of joules, which would be scientific notation with a 3 or 4 exponent. But if we take a 1 kilogram object and we make it go this fast, then let's see what kind of scientific notation that's going to end up with. So I'm running a little low on space. We'll bring this up in the corner. But kinetic energy is 1/2 mass times velocity squared. If we use the mass is 1 kilogram, then that's kind of nice here. Oops, I can't write today. We've got 1/2, which is just 1/2 or 0.5. Then the mass is 1 kilogram, and the velocity is this thing down here that's even still technically rounded. But it's so big, these aren't going to make much of a difference in the end. We're still just going to have an astronomically huge number. Okay, so the nice thing about this 1 is it doesn't really factor in. We basically just need to square this number. In fact, the 1/2 in front is going to have a bigger effect on the answer. But, square this number up. Kilograms times meter squared over second squared, as it turns out, is just what makes joules. And this ends up being really close to 4.5 for the number in front. We get something like 4.4999. and then 10 to the 16 joules. So a billion is 10 to the 9, a trillion is 10 to the 12, a quadrillion is 10 to the 5. So it's like 45 quadrillion joules. It's an unbelievably massive number. All right, but that's it.